Hey, welcome to the Toolkit channel. So past couple of episodes I have discussed about Cuda core distributed parallel computing, and I've also discussed about NVIDIA Toolkit to do massive parallel compute so that you can offload whatever you do on a CPU onto a GPU with this Cuda toolkit provided by NVIDIA. So as a part of the first episode I have discussed about the GLmark benchmark. So with that you can test the performance and the ability of your Cuda processor core with that given GPU card in a Linux system. And in the other episode I have discussed about GPU stuttering and whatever issues I am facing with my system, and I have also showed you after I did an upgrade of the hardware, I can see the performance benchmark directly from the old outdated GeForce 210 to GeForce GT 710 NVIDIA GPU. Although this GPU itself is also quite old, it doesn't matter because I don't use this system to play any games. I may just use this for basic video render like this YouTube videos, and as well as apart from that I'll use it for maybe down the line in future for this kind of parallel compute and other such research purposes. So today what I did is like I mentioned in the previous episodes, I have come up with a code wherein we can do this offload and then we can test how it performs with a CUDA offload versus something you do traditionally on a CPU based platform. So this is the code I have come up. This code is based on this NVIDIA guide, so I have included all the references. It's based on that guide. One problem is the guide have the portions of the code, you need to summarize everything and then you need to make it work. So that's what it is. So this is the guide. You can see here, this is from the NVIDIA. So there are some main important references I have included. One is this, and the other one is this programming guide, and the other one is another section of that programming guide. And apart from that I found this interesting book as well. So you can see here it's a large book, it's around 527 pages. So it's quite interesting. What I'm going to do is I'm going to share this sample code, and inside the sample code you can find all that references and as well as this main guide from NVIDIA, which is Introduction to Cuda programming part. You can see here it is through C or C++ how you can do Cuda programming so that you can offload a traditional code onto this GPU platform. So it is quite very useful to start with. I found this guide is a must to refer to start with than any other sources. You can see here as you go through, they have also incorporated very good architectural diagrams and other stuff. So I just want to point to you guys whichever is existing in the guide. I don't want to much discuss. However, in this context of this video I just want to mention a couple of things before we dive into the code so that you can understand what exactly I am talking about. So one of the important things you have to understand is the terminology of host and device. What NVIDIA proposes is whenever you call this system as a host, it is your RAM processor on your motherboard. The general CPU, generic computing platform is what is called as host, and whenever you use a dedicated GPU card, they refer that as a device. So even the GPU card is going to have a processor, the GPU processor with hundreds of cores, GPU cores, CUDA cores, versus a CPU which may have like as you know 4 or 6 or 8 cores or something like that. If it is a Xeon, maybe 30 cores or something like that. So that's what they try to distinguish. One is your host, the other one is your device. Whenever they tell device in this guide, which means your GPU card, which is also treated as a separate computer. So this you should bear in mind, because this is when it helps this nomenclature to understand how you architect your code, because anytime you need to push your code from CPU context to GPU context, it means that you are pushing the code from host to device context and back again. Whenever you are getting back that results stored onto your GPU memory, you need to pull to the regular memory or RAM, then you need to pull that from device to the host. So that's the nomenclature. So that's what this slide is all about. So other than that, it is quite interesting. They kind of mention that in a host, things happens in a serial manner, and obviously whenever you do some vector calculation or some array computation or something like that, things will happen in parallel mode. And even though you have multi-threaded applications, it is sort of, each thread happens in a serial mode. So that's what it is, versus if you kind of offload it to the Cuda processor, Cuda cores, you can almost parallelize, you can do some massive parallelization and HPC and stuff like that. So this is a very simple guide. It is very good for beginners. I highly recommend you to first go through, and when you are watching my video, I suggest you to parallelly open this guide and also go through whatever it is mentioned over there. So you can see here they have mentioned all these cool diagrams. I don't want to explain too much, which is obviously in the guide. And when you start referring about the code, you can see here this is where it starts. They mentioned this hello world, and they have also mentioned how you can compile and other steps. So here is where it sort of starts. So as you can understand, as I said earlier, in the guide, it is all spread across in multiple pages, and what I did is I have merged all of them into a working code, and I have made one example, and then I have made another variant or another example, so that we can do this parallelization with the second example. In the first example, you can just do a basic proof of concept where you can run a piece of code in a GPU. Let's not waste any more time on this guide, because this is what I mentioned. This is the source of my code. I don't want to take any credit. I just did a nice packaging of the same. And in the second variant, of course, I have added some few APIs here and there myself, which is not in the guide. So coming back to this first simple example, you can see here it's a very simple example. The objective is you have three variables I have mentioned in a slide so that we can understand the scenario. So we take this as the first example. You can see here it is a very simple stuff. You have two variables, and we are adding these two variables and saving it in the variable C. So instead of doing this on a CPU with your regular C code, we are trying to attempt it in a GPU. So this is a sort of not a good example to do, because this is not a GPU meant for. So anyway, this is just a proof of concept, and also you should understand if there is any installation error or device driver error or something like that, this code may not work. So this was not working earlier in my systems. Then I was debugging, and finally I made that SDK and Toolkit working properly in this system. So bear that in mind. This may work and may not work. If it doesn't work, check your device drivers, check your NVIDIA install packages and other stuff. Again, this is something you can get it in that documentation over there. You need to install that SDK. And finally you will get that stuff. So make sure you install them everything properly, and in case if you install, you should get this working, and in case if there are any errors, you can catch over here. So this is something extra I have added. I was going through various discussion forums, and I have added this particular piece. So as I said, this is a derived code. I have added my stuff, but the basic code is something I got it from the guide. So getting back to this, you can see here it is very simple. You have these three variables. You can directly do int a, b, c, and then you can do a plus b equal to c, but c equal to a plus b, sorry. So instead of doing that, what we are doing is we are trying to push this variable context into the device, which means the GPU card, as they mentioned. So for that, we have these three pointers. So you can see here these are not allocated in the CPU context. So this is what it is: device underscore a, device underscore b, device underscore c, and then you can jump directly here. You can just ignore this portion. As I said, I was getting some errors, so I inserted this code after going through various discussion forums, and I was cracking out what the error code means and other stuff. So in case if it is not working on your system, this may help. So you can just ignore this portion, so you can jump directly here. Since these three variables are not initialized, we are initializing in the device, not in the host. So not in the CPU, not in your regular memory. So in the device you are allocating the memory space. So that is why you are using this API Cuda malloc. So with this it is assigned with the memory space. You can see A, B and C, device underscore A, device underscore B, device underscore C, all of them are getting memory allocated within this device. So with this this variables in the device is ready. So now the next step left is you need to have a mechanism to copy this variables which is A, B and C in the CPU context to the device context before you perform any operation in the device context, so that you add that device underscore A, D underscore A and D underscore B, and then you add these two and then store it into device underscore C. So before that we are doing a Cuda mem copy because this is not your regular assignment. So you are doing a mem copy, a very simple mem copy, and as you can see it is quite simple. Device underscore A, and you are passing this A. Since here A is a simple variable versus D underscore A is already a pointer, so you don't need to mention anything address here, so it's simple. So end of A, and then you are mentioning the size, and you are mentioning this operational parameter. So you are mentioning that it is Cuda mem copy host to device. So this is required for that API, so we just need to pass that, that's it. Okay, so in this case you are passing the same. So Cuda mem copy we have done for both variables, so which means now the A, B is whatever is in the CPU context, the same values are being assigned to this device context as well. So that's what it is. So this memory space in the device is a memory space in your GPU card, and this is the memory space I was discussing in the previous videos. Whenever you buy a graphics card, you may have it memory specifications like GDDR5 and stuff like that. They may mention 2 GB and stuff like that, which means it's a memory in the GPU. And GDDR, it means it's like a graphics variant of DDR memory. Sometimes you may find like GDDR5 or something, very common these days, which means it's a variant of graphic card memory. So that is nothing to be confused with your DDR4 memory, because we don't have any DDR5 memory modules yet for a PC platform or generic compute platform. So that's what it is. So you can see here Cuda mem copy. With this it is over, and then this is the next important construct where you can use. So add, and then there is a specific nomenclature 1, 1, and this denotes how many instances and stuff like that. I'm going to shortly tell the same. So this you need to do, and this add is nothing but your function over here, and this you can see here it's a generic regular function. You have 3 pointers, and inside it is doing again an addition of that star A and star B, and it is storing to that value of pointer C, which is star C. So it is fairly simple, and with that it is over. And once it is over, the value of C, which is device underscore C, is in the Cuda processor in the GPU memory. So from the GPU memory we need to pull it out to the CPU context. It's just optional, we can even display, I think so, but again you need better if you do any printf or something like that, you need to pull it to the regular context. So which is why we are again using this mem copy, and in this case we are storing it in C. You can see here end of C, and we are pulling it from the device D underscore C. And then here is the operation. You can see here it is reversed. Here in this case it is mentioned as Cuda mem copy device to the host. So that's what it is. And after that I am doing a simple test print to check whether it has worked or not, because this is just a simple variable. We can do a simple printf and then we can check the same, and after that you can do a cleanup, because here there is a memory allocation. So we can run this example and we can find the output. So I did this small compile script like I do in my most of my sample code. You can see here it is quite interesting. You use this compiler as NVCC, not the regular GCC. So NVIDIA CC is the compiler of that SDK or whatever toolkit, and you need to pass all these options, and then it's like any other compilation. So you pass this final binary file name and then the source file name. So you can just compile the same. Let me do once again, although it is compiled earlier. So you can see here it has generated the source. So we can run this first example, Cuda hello world 1. Yeah, you can see here before it has A is 2, B is 7, and then C is not having any value, and after it is pushed to the device, and device have computed, and we have pulled back that D_C to C, and we got this result as 9. So which means this SDK is working first. So that's what you need to confirm. As I said, it may have some issues. You need to check your installation. You need to also check your NVIDIA device drivers and stuff like that. This is something I have mentioned in the previous episode. You have proprietary drivers and other stuff. So check with that. In case if it is not working, you need to check sometime if everything is set properly according to the guide. So you can see here, which means that this particular entire proof of concept is working, your SDK, everything is fine. So now let's go back to the important part, which is this second sample. This is why we need some kind of, parallel compute platform. So this is the main important part. So I did a small slide to depict the same. So here our objective is, we have this array which is A, and we have another array which is B, and the objective is copy from A of 0 and B of 0 and store it in C of 0, and we need to repeat this for as long as the size of that array. You can imagine this can be some vector compute, or this can be some kind of matrix calculations and stuff like that, because this is what something you need quite often for any games and other graphics intensive polygon rendering and other stuff. So this is something, although it is used in games, this is very useful in case if you are using this for scientific applications. You need to do some kind of HPC, high performance compute, for some supercompute complex modeling and stuff like that. You need to compute various data points, and you need to compute some kind of weather patterns, or some applications like astronomy and various such scientific applications. It will be quite useful. It can be also used for any encryption and other such applications and compression and stuff like that. It can be, of course, that's why this is the reason this is also used for crypto and blockchain technology, because you need to do something which is quite repetitive for several data points. So this is where we can parallelize this. You can imagine this particular code, if you do in a regular CPU, you need to invoke some kind of a for loop, and the for loop you need to invoke for n number of iterations, and it is going to do in a serial manner. So it is something you can't parallelize this particular stuff. Of course, you can split into, if this array have a million rows, maybe you can chop into several segments, and each segments you can push into a thread, and then each thread the CPU can handle. You can do all sorts of tricks. Okay, I'm not denying that. But in a simple scenario, you need to have a for loop, very simple, and you need to do this again and again, over and over, several iterations. And this is a serial computing context. This is nowhere it is going to be a parallel compute logic. So this is what you can parallelize it using Cuda programming. So that's what is the main significance of this scenario or this sample. So to an extent, they have also mentioned this in the guide a little bit. You can go down, although they have not so much glorified like I glorified here. You can see here a similar thing they have mentioned, and again code they have put bits and pieces, and it takes some amount of time to understand what they are mentioning. So after they mentioned that, somewhere here they have given a example. So this is what I was like, everything I collected and I neatly put inside. So but anyway, nevertheless, it is quite useful. This guide is really useful. It really have inspired me, and I was quite curious to try Cuda compute in my other projects as well, not even just Toffee but any sort of client specific systems architectural stuff. So I may do sometime down the line for Toffee as well. I need to do some massive parallel packet processing. I'm thinking to automate, I'm thinking to sort of parallelize that and push onto the Cuda cores than CPU cores. Currently anytime packets come, I need to allocate CPU threads, and it's quite CPU intensive. So I think I can offload it to this Cuda cores, but it's quite tricky, but because the code is very complicated, so I need to see how I can port such stuff which is existing as of now onto this new platform. So that's what. So we can jump to the code. You can see here the code is very simple. They mentioned define n is 512, so which is an example. You can find it over here. Yeah, you can see here. From here it starts. Somewhere here, they mentioned the code. So it is again in bits and pieces, so which I just collected and put across over here. So as you can see here, you have an array of 512 elements. So we have in the place of int just a, b and c, we have this int a, b and c in array form. Each one is an array, you can see here, and below that we have this once again for device context as well, d underscore a, d underscore b and d underscore c. And after that, here is the Cuda malloc, and here again we are doing the same thing. Here there is a small difference because earlier example we are not having anything like an array, it is just a single integer value, so it is just a size of int, which is this size, versus here what they have done is int size equal to n times of size of int. So it is multi-dimensional versus the earlier example. So Cuda malloc of that multi-dimensional size, instead of just size of int, it is n times of size of int. So it's been allocated for a, b and c, device of a, b and c. So below that it is quite simple. We are doing a malloc of this a, b and c of host as well, because this is not a simple variable like the previous example. Apart from that, they used anonymous API as random bits, random ints. I thought this random ints is a standard API or something. Then I came to know just they used some examples, so which is we need to have some common sense to fill that API. So I have just coded that API. Couple of things I have done is although they mentioned random means of a to n, I have just did this random max so that I can define something, I can just set the limit for this random integer. Otherwise it is giving a large value, something like 10 digits or something like that. I don't need such large integer values. I just need something to test this theory. So I did added this extra stuff to this random means so that I can define this range. So you can see here rand percentage rand of max, I can tell 10, and then it can give random numbers from 0 to 9. I can give 100, it can give random numbers from 0 to 99. So this is quite useful when you need to quickly compare and check whether it is all working, so rather than taking a very large integer random number. So I'm passing over here because the reason I said is, in case if you are going through this guide, there may be few changes you can see here and there. This is the reason I added that extra stuff. So I'm passing this limit for that random number, and we don't need it for this C array, because this is the array which we need to get the values back. I just added this debug API print array, and we can just print some 3 to 4 instances of that array, so that to check and compare whether it is all working. So I just hard coded as 3 values instead of big for loop and displaying all that n elements of that entire array. So this is what is this print array is. So I'm printing the array for A and B. So after that, you can see here we have once again this memcopy, so that we can copy from host to device. you can see here it is just the same as before, except we pass the size, and this size is multi-dimensional. So after that we are passing this, we are calling this add API. You can see here there is a small change. We are mentioning this is for n elements, and then we are passing these 3 pointers. And you can see here there's a small difference in this add API. You can see here blockIdx.x and blockIdx.x and blockIdx.x. So this is what it parallelizes. You don't need any for loop, nothing as such. So this is why it is such a nomenclature. Again, you need to go through the guide because it is a part of the SDK. So that's what it is. So go through the guide. I don't want to go much in depth about each and every stuff. There is a lot of things. From here it gets very complicated. If it is multi-dimensional, again you need to do certain things again. So I don't need to go much in depth. The more examples they provide in that SDK toolkit guide, you can understand subsequently once you do one after another level. So you can see here it's computed, and in this case it is done one shot in parallel using the Cuda course, not any for loops, no such nonsense. So it's all taken care and it is all done automatically in parallel. So this is where if you inspect you can save a lot of CPU cycles. Imagine this array have around 1 billion entries. Then what happens when you do a for loop or something like that? Although if not that, maybe you may have some indexing scheme and you try to parallelize, still it is going to consume it will involve a lot of CPU cycles, and it is end of the day still a serial process versus as much as possible you can parallelize the same using this Cuda offload. So that's about it. So you can see here once everything is done, once again we are copying that d_c from device to the host, and then we are printing this array using this API which I have written. So after that we are doing a cleanup for both arrays, because it's an array we need it for A, B and C as well, which is not this line you don't find it in the previous code. So what we can do is we can quickly run the same, and we can see how this one will produce the output. You can see here these A of 0 and 1 and 2 is random numbers. It has 3, 6 and 7, and B of 0, 1 and 2 are 7, 4 and 0. You can see here since 7 plus 3 is 10 and 6 plus 4 is 10 and 7 plus 0 is 7, you can see here C of 0, 1 and 2. So instead of printing all that 512 values or elements in that array, I'm just printing that first 3 elements to confirm it's all working fine. So this confirms that this is all working fine, and I have not done any sort of benchmarking and all with something like a logic like this, versus avoiding this logic and do a simple for loop and iterating it for several thousands of iterations or even around 1 million iterations, and compare which is faster and how is the performance difference between doing everything in a host, which means CPU and RAM, versus doing the critical work, whatever the main logic in a GPU, and then getting back to the host and then further consuming that whatever has been computed by the GPU. So it's very interesting. As I said, it's have very good scientific implications. So this is very important in case if you are into some scientific research, you want to iterate something over 1 million times, and it can be even used for some sort of database batch processing and various things like that. So it is very interesting, and that's what I was quite busy these days doing several experiments and also trying to incorporate in my code as well, so that it will be useful for some kind of data center applications where I can leverage and I can use a very good Cuda compute platform. Sometimes you can integrate multiple gaming cards, and then you can use everything in parallel, all of this Cuda cores So it's quite interesting research. I thought let me just share in case if you are new, it is very new, and the first challenge is getting the setup up, and the second challenge is understanding the big picture. So I thought let me give the big picture and also let me show a working demo so that it kind of inspires you to get into something like this. It's just GPU and gaming cards is not just for gaming alone. It is quite useful for these kind of tricky scientific applications where you need to deal with billions and billions of data points, something even like what CERN does. Each time they generate several GBs of data or TBs of data, and they need to process this data even to get anything valuable out of their scientific research. So that's what it is. So what I'm going to do is I'm going to bundle this source code with the compile script and the binaries which I compiled at my end, and I'm going to add it to this page, and you can find the video description to this page so that you can also download the source. And as I said, you can use all this references and the links I have mentioned over here. I'm going to also mention this in the website as well, so that it is going to be useful for you in case you want to do any further experiments. And kindly go through the guide. It has various other examples. They have various other examples apart from this. As you can see, indexing, and even I think they have also mentioned about multi-dimensional arrays and stuff like that. So I suggest you to go through the same, as you can understand each concept much more advanced than what they discussed before. So if you get that flow, it is good. You can do all the experiments even before you attempt to architect anything of your own, or trying to adapt something like this in your production systems. So with this, I would like to conclude this video. Hope you guys loved watching the same. If you have anything to discuss, be in touch via mail. Thanks a lot for joining me. Stay tuned. Have a nice day. Bye bye.